Okay, so this is a gas-centric view of a refinery, because that's what we're most interested in. There are really most refineries, particularly modern-day refineries, cannot operate without very carefully controlling gases throughout their operations. And so this is advantageous for us. You see up here there's a sort of a recovered hydrogen and refinery off gas, a lot of gas processing right in refineries. All these places here where you see hydrogen, they're using hydrogen. They're purposely treating fractions to get rid of sulfur and things. We'll talk about that. And then some of the products, of course, LPG, the olefins, and that some of the fuel gas, those are all gases that they have to control. Some of them are products that they resell. And in some cases, the reactions make chemical feedstocks as well, so which will tie into the next presentation on petrochemical work. So what's going on in here? The crude oil comes in, and so it's a heavy liquid. It's a very complex mixture, and they have to start fractionating it. Yesterday, we talked about fractionation of natural gas liquids. Well, that's a much smaller number of potential molecules in there. So here you're talking about compounds instead of C1 through C6, you're talking C1 through C80, or some astronomical, high, monster large asphalt type molecules. And what they do as they feed this in, they use a thermal fractionation. Yesterday we used compression and cold temperatures to fractionate the gases. In the liquid, in order to generate and break the thing apart, it's usually a thermal distillation to start, and there may be a vacuum distillation as well after that to further separate it. So up here you have some of the very light gases and naphtha. Now you're getting the kerosene, gas oil, lubricant, and you see as you go up in molecular weight, you need higher and higher temperatures to fractionate it and drive them apart. And the fractions in this case, and not like a separate demethanizer, a separate depropanizer, they're basically cuts. So it's not a single, like in the natural gas processing, there was methane and then ethane. In this case, with thermal fractionation, you're getting like a grouping of similar molecular weight and volatility molecules come on. They get further treated and separated elsewhere in the refinery, but the incoming step is break them up and then send them to the right place in the refinery. So where are some of the most important areas for us where we have application, where customers will be interested in talking to us about this? Well, in the gas processing area, the olefins and refinery, and fuel gas is a major one that we'll talk about. You see some of these go right to the petrochemical or LPG. Some countries LPG is used as a fuel quite a bit. Mexico, some places in India and places, but not in other cases it's used as a feedstock or other maybe a heating product. But catalytic reformers, they make a variety of products called reformates. Some of it goes to blending gasoline, and others aromatic compounds like xylene, and as building blocks for chemicals. And then the fluid catalytic cracker, in the process of, that's another cracking or fractionation process there, right? And what comes out of that is of interest to us, some of the gases that they can get are propane and propylene. And again, those are valuable for chemical feedstocks or other fuel. Alkylation is another process unit here where they're doing a conversion with usually a liquid catalyst. And what that allows is they make what they call a fuel alkylate. So it boosts octane for like aviation fuel, for gasoline. So and the reason they do that because they're trying to increase the octane level without using oxygenates, which cause ozone and other pollution problems. So the alkylate is a good way to achieve that higher performance with less pollution. Yeah, so anyway, so what do we offer in here that where we have well-defined applications? Well, there are process control measurements, there are product quality measurements, and then there are environmental compliance ones. So we'll get into some of these, like the catalytic reformers, alkylation, fluid catalytic cracker, hydrotreating, and then refinery off-gas, and fuel gas and flare gas. Virtually every country that has a refinery will have some sort of environmental regulation. They just can't just put up anything, and it's very common to have requests, and it's one of the bigger applications we get. So, okay, so we'll start just after the fractionation. You have naphtha, you have gas oil thing. You fractionate it, but you haven't gotten rid of the sulfur and other contaminants in there. So one of the first things they have to do more and more in refineries, the good sweet oil that comes out of the ground with low levels of sulfur compound, those are being depleted, and they're having to use lower quality feed crude oils, and in doing that they got to treat them more to make clean fuels at the end of the process. So that's what hydrotreating is aimed at doing here. So, and here you see, here's that atmospheric distillation, so that's the crude oil coming in, and it's giving off all these fractions. And then they have to hydrotreat it and clean it up before they start doing other refining. The reason is that a lot of these other processes have catalysts that would be very sensitive to these type of compounds, and if they didn't remove them, when the fuel was combusted, it would give SO2 pollution and violations of the plant's environmental permit, and then it wouldn't be acceptable for a clean diesel or clean gasoline work. And you also the vacuum distillation, as you get to the heavier and heavier leftovers, the asphalts and the heavy, really thick, viscous material, what you need to do there in that resid is draw vacuum on it to help the fractionation, because at atmospheric conditions alone, there's not enough to drive that fractionation there. And those things need to be hydrotreated too before the streams progress for further refining. So, okay, so this is just giving an idea of some of the organic compounds in petroleum. See, all the carbon atoms. You see methane and natural gas with some of the things we were talking about yesterday. Now at the far end, tar and asphaltene things. So the complexity and just the sheer molecular weight size of the molecule is enormous. But what you also see included in here are what they call heteroatoms. So the heteroatom will be something other than carbon or hydrogen. So you might see nitrogen and sulfur. Those are concerns, particularly sulfur. Oxygen can be a problem as well, but this is the big one that refineries have to do something about. So, and this little table here is giving you an idea of the relative composition, a nominal composition of a crude oil. So you see carbon is the predominant element found there, hydrogen, but sulfur, depending on the source of the crude oil, can be up as much as 6% of the weight of what's coming in the feedstock. So nitrogen is an issue, but then some of these others, nickel and vanadium are we don't do that type of spectroscopy, but the people running the refinery will take a sample, bring it to the lab, and look for those too, because those poison catalysts as well. Okay. So what are they? We showed you that there are sulfur atoms there. What are the compounds that are commonly encountered that they need to do something about? So they have thiophenes, a variety of them, and then they just keep going up in size and complexity of the aromatic ring structure. And what do they do about those when they're there? So R is just like a generic molecule, like a mercaptan or a thiophene of someone. So some sort of sulfur compound. R is just like a placeholder, if you want to call it that, for representing molecules. By adding hydrogen over a catalyst and heating it, there will be generating some sort of hydrogen based compound, and they're actually making H2S. They're converting the sulfur compound, and in the refinery, they make H2S. In the natural gas world, the H2S is already there. It's coming out, it's in the actual gas. Here, the maniacs in the refinery are creating H2S, and a lot of it, but they're doing it on purpose. And then a similar reaction, at the same time you're doing this, any nitrogen compound would be forming ammonia. That's also going on at the same time, but they don't really worry about that in terms of the fuel or the products they're making, but it can be a concern from a corrosion problem if it's a high nitrogen crude oil source. Okay, so depending on what molecules are there, right, thio to like some of these very large or benzodiophene, you see where they come out, where they concentrate in the fraction. The lighter weight ones, thiophenes and thiols, gasoline, jet fuel, and then as you get to diesel. So the larger the molecule structure, the more difficult it is to break up the molecule, grab the sulfur molecule and make H2S. So it's just more and more difficult. It's easier to break some of these bonds than it is, as you get, they're more hindered from being broken. So, okay, so this is a very important operation in refineries, and the refinery operators settle on certain types of processes from different licensors based on the products they're making. So they have to use this. So, and here are some of the customers that we're licensors rather that we have encountered that customers are using. We at Endress and Hauser have started a process licensor initiative. It's part of the oil and gas group, and we are targeting Axens and UOP as the first ones for hydrotreating to go in and get a whole cross-section of products from Endress and Hauser and Spectra Sensors on their approved vendor list. So that's our ultimate goal, and that this is unfolding right now. So we looked at all the different refinery operations, and so there's some nice high-level marketing activity to go in and get these things approved. So.